Okay, welcome back. In the previous video, we laid the groundwork for understanding where nuclear energy comes from by discussing the strong force. So we first of all we I think you have a better appreciation for how weird it is that we can have elements beyond hydrogen, things like helium or lithium, carbon, and so on, where you have multiple protons, which are all positively charged, and yet somehow they're able to live together in very close proximity to each other in a nucleus. And I hope you appreciate better now just how strange that is. We know that like charges repel, so if you have all those positively charged particles, very close to each other, why in the world don't they just fly apart, right? Well, now we know that there's a fundamental force in nature called the strong force. In some textbooks, you'll see it referred to as the nuclear force. And at very, very close distances, if you can get those nucleons close enough together, the strong force takes over. It overpowers the electrostatic repulsion, and it holds those nucleons together very, very strongly. And that's the key. That's the source of the nuclear energy. And so now we're in a position to delve a little more deeply into that, and talk about Einstein's contribution to this whole thing. All right, so consider again this atom of helium-4. All right, and remember in this isotope notation, the superscript is the mass number. That's just the total protons and neutrons, and the subscript, that's how many protons are in the nucleus. Okay, so if we were going to play Master of the Universe and we were going to make one atom of helium-4 from scratch, all right, you would need, what ingredients would you need? Well, you need 2 protons. We've got those over here. We need 2 neutrons. We've got those over here. And then I've got the electrons. They're ready to go. They're in position. Okay. Now, in order to understand what's going on with nuclear energy, the first thing that you have to notice is what's going on with the mass. Let me just lay a couple things on the table here. It is known, the mass of a single proton is known to very high precision in terms of atomic mass units, and this is the value for protons. Here's the corresponding value for mass for neutrons, and you can see, they're very similar in mass, but the neutron is just slightly more massive. The electrons, as we go through this analysis, we're going to exclude their contribution to mass, because electrons they do have mass and it does contribute, but they are very, very small compared to the neutron and proton. Okay, so for simplicity, we will exclude those from the analysis. All right, so here's the question in green. If we were to, from fresh ingredients, protons and neutrons, we wanted to make one atom of helium-4, and now that you know the mass of the proton and the neutron, can you tell me what will the mass be of the complete atom once it's put together? All right, so what I want you to do is pause the video now and do that calculation. Okay, hopefully you set things up like this. So obviously we have 2 protons, and they each have this mass in atomic mass units. Likewise, 2 neutrons with their mass. And when you do the math, this is the total mass of the helium-4 that you should come up with in terms of atomic mass units. Okay, so all well and good. Now, here's where things get a little strange. Just like scientists are able to very precisely measure the mass of the individual proton and neutron, they are also able to measure the mass of a single atom. can do that with high precision as well. And as you can imagine, they've done this for helium-4, and here's what they got. So we put everything together, they measure the mass, and they got 4.002603 AMU. Now, obviously, the thing that jumps out is that these two numbers are, they're similar, but they're, strikingly different. The mass that we expected to find when we put everything together to make the complete atom is quite different from from the mass that you actually measure. And so, what's going on here? That's very weird. Okay, so let's just to kind of restate this. I'm gonna frame this as a nuclear reaction. So I'm going to write the equation for the nuclear reaction. So here we have 2 protons, 2 neutrons, and guys, don't worry yet. This is a very specialized notation for representing protons and neutrons, and we're going to learn about this, but don't worry about the details for now. Okay, so here they are. Here are the reactants, the nuclear reactants, if you will, and we saw that the total mass of those 4 nucleons was this. We, quote, react them by fusing them together into a single atom, and this is the mass that we actually find after the nuclear reaction. So, and here's the mass that has gone missing. All right, so this was like a little weight loss program for helium. It's reduced its mass by this much. So the question is, what's going on? We've heard before that mass is conserved, but in this case, that doesn't seem to be the case, right? So what's going on? Okay, well, watch closely. What actually happens is when you I'm sorry, before I go to the next thing, this lost mass, this mass that has gone unaccounted for, is known as the mass defect. And so that's a term that I want you to be familiar with. You gotta know what that is. So the mass defect is simply the difference in the mass between the constituent particles and then the single atom. All right. So many times there's going to be a discrepancy here, and that's called the mass defect. Okay, so if we look closely, when we put those together, did you see that little lightning bolt come out of there? Let's see that again. All right, when you fuse, and by the way, this is what we would call a fusion reaction, because we're fusing smaller particles together to form a large particle. When you do nuclear fusion, energy is released. And that is very closely related to this mass defect. And in fact, the energy that's released is typically in the form of gamma rays, which are very, very high energy radioactivity, and we'll be learning about those very soon as well. So again, you have been told probably your entire science career, isn't mass supposed to be conserved? Well, not when nuclear reactions are involved. It's a different ball game. Also, you've probably heard this phrase, a few times. The whole is greater than the sum of its parts. Well, I think you can see in this situation, this is definitely not true. It is, in fact, it is the exact opposite. The whole, okay, when you put those nucleons together to form a helium atom, the whole mass is less than the sum of its constituent particles. Okay, now what you should also know about the mass defect is that in any sort of physical process, like, or I should say nuclear process, when mass is lost, energy is released, and that's an exothermic process. The mass and the energy that are involved here can be related to each other through Einstein's most famous equation, E equals mc squared. And I know you've seen that many times before, but maybe you haven't actually used it. But we're going to use this to actually do some calculations. Now, there's a couple pieces that we need to put into place before you'll be comfortable doing these calculations. One is, see here we've been talking about a single atom, and we've been talking about atomic mass units, right? But for these kind of energies to be usable, either for nuclear power or for nuclear weapons, we have to have a larger quantities. You have to have a lot of these atoms undergoing fusion or fission. And so we're going to talk about 1 mole. So we need to figure out what would the total mass defect be, not just for one atom, but if we had 1 mole of helium-4 atoms that were being created from their constituent nucleons. And then, and this is a trivial thing, we're going to need to convert that mass for 1 mole into kilograms. All right. Okay. Now, so I want you to follow this as closely as you can. For this, you don't need to take notes so much, but just really sort of concentrate and try to let this sink in. I'm going to try to demonstrate for you the relationship between atomic mass units and grams. Okay, so you've got your periodic table there at the ready. I want you to tell me, what is the atomic weight of hydrogen in terms of AMU? Okay, now your table probably says 1.008, but to a little higher precision, it's known that the atomic weight of hydrogen is 1.00794 AMU. Okay, fine. Now, here's my question. We'll take this as the atomic weight of hydrogen. Now, if we had 1 mole of hydrogen atoms, how many grams would that be? So hopefully you're remembering, the fact that when if you're asked how many grams is 1 mole of any element, you just take that element's atomic weight, and that is the mass in grams for 1 mole of that. Okay, so far no trickery. This is all old stuff, right? Okay. Now, what I've done here is I'm simply taking that single hydrogen atom, and I'm just substituting its mass in AMU. Okay, so that's we've agreed at step 1 that 1 hydrogen, the atomic weight of hydrogen is this. So I'm just going to put that in here into the parentheses instead of hydrogen. Okay, so what this means, so if you think about this, if you have 1 mole, that is Avogadro's number of particles, where each particle has this mass in AMU, then you have that same number of grams. Okay, so if we had a particle, let's say we have a hypothetical particle that instead of has this kind of bizarre number, it's a very simple number, 1 AMU. So my question is, if you had 1 mole of particles, each particle having a mass of 1 AMU, how many grams would that be? Well, hopefully you can see the pattern here. It's just the same number, right? So this is like my little proof. If you have 1 mole of particles that are 1 AMU, then that's going to be 1 gram. All right. So so keep that. This you need to write down in your notebook. Okay, 1 mole of 1 AMU equals 1 gram, and that's by definition. Okay, now moving on. So we just saw that when we created 1 atom of helium-4 through the fusion of 2 neutrons and 2 protons, we lost this much mass. That was the mass defect. So my question is, if we were to create 1 mole of helium-4 atoms, how many grams would our mass defect be? And hopefully, now that we've been through this, you can see that it's the same number, but we just change AMU to grams. Okay? All right. Now, so 1 mole of this is equal to that many grams. Now we're in a position to use Einstein's equation E equals mc squared to figure out like how much energy would be released if we took, if we created 1 mole of helium-4 atoms using the fusion process based on this amount of mass that will go missing. Okay, so c is the speed of light. You've probably seen that before. And here's the actual value. The speed of light is 3 times 10 to the 8th meters per second. So that's 300 million meters per second. And that speed gets squared. Okay, so this is going to be a really big number by the time we're done with it. And then we just take that mass, this is the mass defect, that converted to energy, and we put that in here. Okay, so listen, if you can, if you want to pause here and kind of review, go back over this slide, just kind of, from top to bottom. If you kind of grab this, you're doing great. You're doing really well. There's a lot going on here. Okay, now, before we can actually calculate the energy, we need to convert these grams to kilograms. And that's trivial, right? We know how to do that. But you might be asking yourself, why kilograms? Why can't I just leave it in grams? All right, well, here's something new that you might need to know. Okay, there's Einstein's equation. The SI unit of energy is the joule, okay? And by definition, 1 joule is equal to 1 kilogram meters squared per seconds squared. Okay, I know this may seem a little bizarre, but just follow me on this. Now, we can rewrite this. We can make a very slight modification, and we can just bring the squared out and apply it to both the numerator and denominator by using parentheses, right? Okay, so this is a little more elegant looking. And this, which is energy, right? Let me go back. So we've agreed that this is 1 joule, and a joule is a form of energy. So energy is equal to this. And that's why we can kind of bring it up there like that. Okay, and I think you can see that why energy equals mc squared, right? The kilogram is a form of mass. Meters per second is speed, right? And then if you square it, so this kind of looks like Einstein's equation, right? Okay, so hopefully you can see that. All right, now let's get back to our calculation. Okay, so this is where we left off. We put this is the amount of mass that disappears during the fusion of when you're making 1 mole of helium-4. And then we're multiplying that by the speed of light squared. First, we got to convert this number of grams to kilograms. All right, check me on this. All right, this is the equivalent mass, but just in kilograms. Now we're in a position to calculate the energy in terms of joules. Okay, so everything's in the SI units now. Kilograms, meters, seconds. All right, so when you square 3 times 10 to the 8th, you get 9 times 10 to the 16th meters squared per second squared. And now I'd like you to pause, and I'd like you to do this calculation and see what you get. All right, hopefully to 3 significant figures, you get 2.64 times 10 to the 12th joules. Guys, I hope you can appreciate what a big number this is. This is a tiny, tiny amount of mass. And when it is converted completely to energy, you get over 2 trillion joules of energy, which is just, I can't even comprehend it. So if you write it in conventional format, that's what that number looks like. Okay, so I've given you a lot of the background story, and now you should be in a position to do an investigation that we're going to start on Tuesday. And here's how it's going to look. I'm going to have a handout for everybody, and it'll look like this. It's going to have the objective. All right, so this is the overall objective. I want you to determine how much TNT, all right, that's an explosive, would you need to detonate to equal the energy that's released from the fusion of 1 mole of helium-4 from its constituent nucleons. Okay, now this is just an example. I'm going to give every group, so you guys are going to work in groups on this. Every group is going to have a different element, a different isotope that they're going to be working with. So don't assume you're going to get helium-4. Very likely you will not. But this is just to illustrate what you're going to do. Now let me jump down here. The final product, okay, what you ultimately will produce from your work is just a short typed report that has these components. You're going to give me, a little introduction that kind of sets the stage for all this with a statement of your objective, an outline of the process that you went through, your calculations in detail, and then a summary of what you found. Okay, now let's go back up. Here's all the resources. You're going to have a lot of support. Chapter 21 in your textbook goes over some of this. You have this web video, which you can go back and refer to whenever you want. I've given you, I'll show you in a minute, where I placed some text from another source on these very concepts, which will help support your work. Obviously, I'll be there to help you, your classmates, and then, gasp, Wikipedia. Wikipedia is actually pretty darn good for science in general, but it has a lot of very helpful reference articles on nuclear energy. Okay, now to get from point A to point B, I tried to break the process down into these guiding questions, and so tomorrow when we start in class, I'm going to expect you guys to sort of follow this trail 1 through 7 in order to build up the the collection of information that you need to produce your short report here. Okay, now one more word about the resources. On my Chem Materials webpage in the atomic structure section, I placed a link right here. So under articles, this one, nuclear binding energy, it's an excerpt from the AP chemistry textbook that we use, which is a very nice source of information. Here's the first page. Here's what it looks like. You'll start right here, section 21.6, energy changes in nuclear reactions. So if you need to, you can start there. I think I'm going to stop there. Okay, guys. So thanks a lot for listening, and I look forward to seeing you guys on Tuesday.